just put some numbers in. So you will be what? You'll be familiar what's going on. So over here, you have two springs, okay? K1 is equal to 1,500 Newton per meter. K2 is equal to 1,000 Newton per meter. Okay? And it's holding a mass. Okay? And the mass over here is equal to 20 kilograms. And then we are going to determine the equation of motion. So we are going to do something a bit different from the previous problem. So from here, we know that spring is under series configuration. So the K equivalent will be equal to what? Will be equal to, by looking at the formula over here, is 1,500 multiplied by 1,000 divided by 1,500 plus by 1,000. Okay. So the equivalent stiffness will be equal to 600 Newton per meter. Okay. Now, if you have a spring, this is interesting, okay? If it's in parallel, if this is 1,500, this is 1,000, right? K equivalent is equal to what? Am I right or am I wrong? If this will be in what? So what does it mean? If you have two springs, if you want to reduce the stiffness of your system, what will you do? Put them in series, right? Let's say you are in a certain place in Timbuktu where you don't have Home Depot, but you have two springs, you want to reduce the stiffness, what do? Put them in what? Series. Okay? And if you want them to be stiffer, put them in what? Parallel. I'm trying to figure out, do I ever see a spring configuration in series? I've not. So this is just for making your life difficult. Are we clear? I know. He said, Eugene, why? Why? So we know that this is, so if we look at the second order, if we look at the second order characteristic equation, we know we have md squared y over dt squared plus by c dy by dt plus by ky, the whole thing is equal to 0. And we know that this whole term is equal to 0. So we definitely have a what? Undamped mechanical system. And the general equation or the general solution, we know there is y as a function of time. So this is equal to C1 cos omega nt plus by C2 sine omega nt. Note for undamped, omega n is used. for underdamped omega D is what? Used. Okay, so that is our omega n. Okay, so from here, we will specify with next we have to calculate omega n, which is equal to our K equivalent divided by our mass. Okay, so our K equivalent over here is equal to what? 600. Our mass 20, so 600 divided by 20. Square root the whole thing, 5.477 radians per second. So we substitute y as a function of time. C1 cos 5.477 t plus by C2 sine 5.477 t. Okay. I'd like to do something different. What is the difference is this? Okay, the boundary condition for this case, okay, I don't always use the same thing. I want to do something different. So when you will not, when you do your term test, you will not be caught in surprise. So the boundary condition is when time is equal to 0, okay, y is equal to 0 meters, okay, dy by dt is equal to, I'm going to put in plus 6 meters per second. Okay. All right. So what it means at this position over here, right, when y equal to 0, right, and or when time is equal to 0, I'm going to impose a velocity. Okay, I'm going to push a velocity, and the pushing hand is going down at 6 meters per second. So something different. Okay. So when we apply boundary condition, t is equal to 0, y is equal to 0, and I'm going to call this is a new example into equation 1. So we know this is 0, C1 cos 5.477 multiplied t, this is 0, plus by C2 sine 5.477 multiplied by 0. Okay, so we know that this term over here is equal to 0, this term equal to 1, so therefore C1 is equal to 0. So C1 is equal to 0, you can drop the term, so therefore y as a function of time, you only need to bother about C2 sine 5.477 t. And then we are going to apply the boundary condition. You know why I dropped the C1, right? Because we have shown that C1 is equal to what? 0. So then we apply the boundary condition. When t is equal to 0, dy by dt is equal to what? 6 meters per second positive. Okay. So from here, dy by dt. So this will be equal to sine to cos 5.477 C2 cos 5.477 t. Okay. So we know that this is 6. This is 5.477 C2 because when t is equal to 0, the whole term is equal to 1. So therefore, C2 is equal to 6 divided by 5.477 is equal to 1.095. Okay. So therefore, the answer y as a function of time, this is equal to 1.095 sine 5.477 t, and this is in meters. Okay. Now, this is the fun part. Okay. How many of you have friends also learning mechanical vibration but not in this class? Yeah, okay. So which class is that? What? It's a 4th year's course. Okay. So when you go to the 4th year course, before you go there, what must you do? You revise what we have taught. Are we clear? So in your 3rd year, if anything to do in your vibration, okay, at least you have some basic what? Concepts. Are we clear? Okay. That's why I do mechanical vibration first. Next. This is going to be the second last part on mechanical vibration that I'm going to teach you. Okay. So the second last part, okay, is going to be forced, okay, undamped, mechanical system. Okay. Now the math will not get any more worse. Okay, you have seen the worst. Not worse. It's too easy for you guys. So what we have now is we have a spring, and then we have a mass. Okay, so we have a K, and now we also declare that Y is coming down. But on this force, or on this case, we are going to put a force function, right, where F is equal to F naught sine omega naught T. Okay? It's a force function. Now, with a force function, you can also have boundary condition when T is equal to 0, Y is equal to 0.2 meters, and Y dot is equal to 0. Okay. You can have this boundary condition also. It's not impossible. But what is different is we have a what? A force. Okay. So how will this force react is if we have a time over here and we have the force over here, because it's a sine wave, you will have a response looking like this. Okay, so this represents your F naught sine omega naught T. Okay, and this will stay on the system. Okay, sorry, this will stay onto the mesh. So in reality, how does this work? It's like putting a flywheel attached to a motor on a cantilever beam. Okay, how many of you know what is a flywheel? How many of you have not a clue what's a flywheel? Don't worry, I'm trying to, over the weekend, I will go to hobby shop to build something for you to visualize, okay? Only if you visualize, you can appreciate this, okay? So from here, right? Now, we are next going to draw the free body diagram. So on the free body diagram, my Y positive is coming down, and then I have a load over here. This is known as F is equal to F naught. Is this red I'm writing on? Yes. Wait. Okay, what's your question? Why the other spring force is equal to what again? Oh, why is it F naught equals sine omega naught T? I like to put that. That's the only reason. I like to, at time 0, no force, and then have a sine